I'm Sahil. I'm your host for the day. I work at a company called Last9, where an observability tool customers like. We've actually been working with Altinity and Josh. So Josh reached out saying if I could help out with hosting today. So here I am. We've got customers like Dream11, MPL, etc. We've been working at scale, and that's where sort of ClickHouse sort of fits into our logs and traces monitoring. And we've done scale observability for customers like Disney Hotstar and Geo as well. So more than anything, here as a customer for Altinity, looking forward to sort of learning from what is happening here. The first talk here is Josh himself. Um, he's a open source dev at advocate at Altinity. He's going to talk about project Antalya. Is that how you pronounce it? Antalya? Yeah, perfect. Altinity's work to bring ClickHouse and Apache Iceberg together to separate compute from storage. If you're building AI applications that need cheap, fast, flexible query at scale, this is the foundation. Josh, all yours.
Thanks, Sahil. And thank you, Nutanix, for hosting us. This is great. As Sahil mentioned, I'm Josh Lee. I'm an open source advocate at Altinity. I'm also one of the organizers for the open source analytics community. We're going to be having a conference in the fall that will be online. So we'll share a link for all of you to join that if you're interested. And this has been great so far. It's my first time in Bangalore doing one of these meetups, and I hope that we'll be back to do many, many more, and that I'll see many of your faces again. As Sahil mentioned, I'm going to be talking about something called Project Antalya, which has been our project to bring ClickHouse to the open lakehouse, right? And we started this project before I think the current AI hype reached the levels that it's at right now. There were some other reasons that I'll talk about why we started this project, but it also turns out that it's very applicable to AI use cases and very, very useful when you're trying to use AI with your data. So I'm going to try and address all of that as we get into this talk. Altinity provides hosting and support for ClickHouse. We have a managed cloud, but we can also run ClickHouse anywhere with enterprise support. We are not affiliated with ClickHouse Incorporated. We're just a different company, although we do contribute heavily to the open source, even though we're a very small company. So raise your hand if you're already familiar with ClickHouse. Anybody? Okay, I see some nodding heads. Awesome. So ClickHouse is a database, right? An OLAP database, and it uses what's called a shared nothing architecture. What this means is that you can scale it horizontally very, very easily because each node has its own memory, its own storage, its own compute, and the workloads are designed to be split up. And basically, we can use horizontal scaling to brute force analytics problems and get answers really, really fast. This is great. And traditional ClickHouse also uses S3 object storage, right, as a destination for pulling and pushing data. But what Project Antalya has been about for us is making that object storage layer actually the primary storage for your ClickHouse database. So here's an example of a traditional real-time event pipeline, right? You might have sources like an observability tool or Kafka or OpenTelemetry. And all of that is going to come into ClickHouse under what's called the merge tree engine. And then from there, you'll be powering things like your real-time dashboards, your APIs for your end user facing tools, and maybe some alerting if you're doing it for observability, right? So this is how ClickHouse works traditionally, and it works really, really well for these use cases. But there are some problems with it that we wanted to address. So here's an example. I flew on an airplane to get here. I flew on actually a few airplanes to get here. There's this data set that we like to use for our examples called OnTime. And OnTime contains a row for every single commercial flight in the world. It gets updated periodically. It's hosted by Amazon. Here you can see an example of a query that we ran on the OnTime data. And you can see that we got the result back in under a second, in 0.6 seconds, for over almost 200 million rows. So this is a little bit impressive, but it's even more impressive when I tell you that we ran this example on a VM with only 4 vCPUs. And basic, no accelerated storage, just the most basic, cheapest form of AWS EBS storage. So ClickHouse is really, really fast. It's a columnar database, And part of the way that it achieves this speed is through that columnar architecture and through that horizontal scaling, that shared nothing architecture that I mentioned. So this particular data set that we ran that query on, if we had to read every column of every single row, it's a 61 gigabyte data set. And if we were using something like a traditional OLTP database, in order to run that query, we would have to scan the entire database, all 61 gigabytes, which would take a lot longer than 0.6 seconds on EBS storage, right? But because it's columnar and because our query only touched 3 of the 109 columns in that data set, that then reduced the amount of data that we needed to scan from 61 gigabytes to 1.5% of that, 937 megabytes. And then because ClickHouse can scale horizontally, we were able to then distribute that to 8 different vCPUs, or 4, sorry, yes, 8 vCPUs. I was wrong. It's not a 4 vCPU node. And each one of those was responsible for reading compressed data, right? Because columnar data, it's all the same scalar type, which means that we can compress it. We can do things like delta encoding that make it even smaller, and we have to scan even less data. So in the end, each thread only needed to read 2 megabytes of data out of that entire 61 gigabyte data set. And that's how we got that answer in 0.6 seconds. This is really, really useful for AI, right? Because ClickHouse now is adding tools that make it very useful as the underlying data storage for AI use cases. One of those tools is vector search, which was just announced as GA in ClickHouse in March. So it's long had some vector capabilities, but they're now approaching usability for like full text search use cases. Of course, this is useful for feeding AI when you can, of course, you can extend the context window. But I don't know if any of you have used the million token context windows, but when I do, it tends to go a little bit crazy. And so it's much better to give it direct access to exactly the data that it needs. And another way that we're doing it, of course, is with the Model Context Protocol. ClickHouse Incorporated has an MCP. Altinity also has an MCP that's available. You can pick and choose. I believe both of them are open source. So you can use whichever one of them you would like with any form of ClickHouse. And then again, that's powering those same real-time dashboards and API access and alerting. This actually creates some new challenges, though, for ClickHouse, right? So I mentioned that if you've been using these tools, right, like Claude is my favorite tool, it can sometimes go a little bit crazy, right? Like if it gets an error that it didn't expect, or if you maybe let the context window get a little bit too large, the thing can kind of start to thrash. And if it's doing that when it has access to a database, it's going to start running queries over and over and over again, right? It's going to really hit that database with load. And these might be very complex queries that are different from any queries that any of your humans are running, because it's being a little bit more creative, right, in how it's working. And so the queries aren't cached, and it's creating a lot of load on the server just for one user. And then you multiply that across all of your users, and you get a tremendous amount of load on your ClickHouse. Challenging, right? But I mentioned we were working on this before AI workloads became a thing. And we had 2 main problems with ClickHouse that we were trying to solve that then turns out actually help with this AI problem as well. One of them is that EBS storage, it's great, but it's really freaking expensive compared to something like S3 object storage. And also, the way that ClickHouse is architected, if you want high availability, you need at least 3 replicas of your data. So you're talking about like storage that's 4 times more expensive, and you need 3 copies. So it ends up being 10 to 12 times as expensive as just using a single copy on object storage. The other problem is that your compute is tied to your storage. And so if you need a certain amount of compute and for your peak times, right, you can't scale that compute down because it's attached to storage that is necessary all the time. Otherwise, you'd be deleting chunks of your database. So we have to scale our compute up to whatever the highest use is, and then we leave that provisioned all the time, which costs a lot of money. So we set out to make this better for our existing customers and also for all of the new customers who wanted this, right? And everything that we're doing under Project Antalya is completely open source. I'll get into exactly how you can get it as we get there. But what we've done is we've essentially, as I mentioned, created S3 as the primary storage layer for ClickHouse. So now instead of each ClickHouse node having its own storage, it maintains a cache. And then it can reach out to the S3 compatible object storage with Iceberg tables and Parquet. I'll get into what each one of those are. And you get this shared data model that can be much cheaper and also much haven't heard of Iceberg, can anyone just like nod if you have heard of Iceberg? All right, cool. So some of you have. For those who have not, Iceberg is really cool. I'm a huge fan of open format, so I'm really, really excited about Iceberg. It's essentially an open table format. So if we think about a traditional database table, the database itself kind of obfuscates and hides from us how that data is actually laid out in storage. Iceberg kind of inverts it, right? And so we have what are usually Parquet files. There are other formats, but Parquet is the most common format. And we put those files, these contain the actual data in columnar format on the object storage. And then in order to query that data, right, because we don't want to scan all of our data every time we want to run a query, we maintain a catalog. And that catalog is just in the form of metadata, right, that tells us what tables exist where and what the file names are to get the data for that table and those columns. And Iceberg uses a commit structure, right? So basically what you do is you write optimistically to the Parquet. Once your writes have finished, you make a single commit to the metadata and create a new version of the entire index. So that gives you something that gives you ACID compliance on top of this blob of storage that is in the object. And it also allows multiple processes to be reading and writing at the same time. It's not quite real time, and I'll get into how we solve that problem for real-time workloads, but it is very, very scalable and very, very cheap. And it's also an open access pattern, which means you can have multiple tools, not just one query engine, but any query engine, ClickHouse, Trino, right? There are many that can read and write from the exact same database tables. So that's really cool too. As I mentioned though, right, Iceberg is not really, in upstream ClickHouse, Iceberg is not considered a primary storage mechanism. It's considered a destination that you would pull or push data to or from. So you would pull the data from your Iceberg catalog into ClickHouse merge tree, do your analytics on it, maybe process or transform it, and then push it back to your Iceberg. What we're doing with Project Antalya is making it the primary storage, but it turns out that these two use cases are pretty compatible, right? What upstream needs and what we need, in a lot of cases, it's the same stuff. It's the same improvements of reading and writing Parquet, working with catalogs, working with vendor-specific implementations of Iceberg, like AWS S3 table buckets, AWS Glue, and things like this. So for the most part, we're all happy and working together, especially on the engineering side of things. Another thing that's really, really important that's come up as these AI workloads have proliferated is single sign-on. So this is another thing that we're working on sort of as a side project on Project Antalya, is we're enabling single sign-on support for ClickHouse. And I mentioned that we're sort of all working together. So here's the relationship of how the code works. We're essentially maintaining a fork. It's really a branch of upstream ClickHouse. We're pushing as much as we can upstream. And then to get access to the stuff that we have that is not in upstream, you can get it from us, from Project Antalya builds, and also you can pull Docker images. So we're hosting these, as I mentioned, it's all open source. You can use it, and you never have to talk to me again if you don't like me. But I hope you will talk to me, even if you don't want to be a customer. So there's a few things that we had to do to make this all work. I kind of hinted at one of them, and it's what we call swarm clusters. So this is the compute storage separation. And basically the way that it works is you have traditional ClickHouse nodes, and those traditional ClickHouse nodes can act as an initiator. You send your query to that node, and it will plan the query and then distribute the query plan to the various swarm cluster nodes. Those swarm cluster nodes then each have their own pipeline to your S3 object storage. So not only can you scale up your compute, but you can scale up your storage bandwidth by scaling out these swarm cluster nodes. And when you're done with your workload, you can scale them back down and delete them because they don't actually hold anything important. They have local storage, but it's only used for caching. That caching also means that in some cases, this architecture can be faster than just using traditional merge tree, which when we, like that kind of blew our mind the first time we ran the test and Iceberg was faster because it's an amazing technology, but it's not usually considered fast, and ClickHouse is very fast. So the use cases, it turns out, are pretty complementary, right? Merge tree is fast, it loads almost instantly. You can do background compaction, which organizes your data so that it's faster to read and write and so that it fits more compactly on storage. And you have very, very low latency to get to that first byte. On the other hand, Iceberg is way cheaper. We get compute storage separation. We can scale horizontally and vertically on a storage or compute independently. We have practically unlimited IO bandwidth. We don't have to worry about things like NVMe drives, right? We can just let Amazon solve that problem for us and give us a pipe to their amazing storage layer. And the other really cool thing about Iceberg is that other applications can read or write from it. So you no longer need to copy your data to work with it with multiple tools. You can just leave it on Iceberg and multiple tools can access the same copy of the data, which again makes things cheaper. We wanted to combine the best of both of these. So in addition to swarm clusters, one of the things that we have created, we're calling hybrid engine or hybrid tables. And hybrid tables essentially use merge tree as your initial layer where your data lands. You get advantage of that background compaction while the data is still in merge tree. And then once the data has typically stabilized, because usually with ClickHouse workloads, right, we're dealing with time-oriented data. So at a certain point, your data will stabilize as the time window passes. It gets compacted, and then it gets transferred over to your Iceberg cold storage where it can be stored much more cheaply. This then enables things like, right, you can use Iceberg for model training without impacting that ingestion pipeline, right? You're not relying on the same nodes for read and write. And so those nodes that are really, really busy in managing your ingestion and doing that background compaction, they don't have to worry about supporting your reads because you can just scale up a swarm cluster or even connect to Iceberg directly from other tools and use that for your large language model training and machine learning. Then, of course, you can have tools like Claude that are accessing the hybrid table through ClickHouse itself so that they can see the most recent data as well as the cold storage data. And the hybrid table kind of hides that from you, right? You don't, as someone querying the data, you don't really have to think about where it is. You just say, you run your query, and the hybrid table will take care of knowing what it needs to pull from merge tree and what it needs to pull from Iceberg. We also want to do some really crazy stuff. So this is something we're calling standalone swarms. So those swarm clusters, right, you can scale up these ephemeral nodes, run queries really, really fast on them. What if the initiator node wasn't another node in the cloud? What if it's just me sitting in a cafe in Amsterdam on my laptop, right? This is something I might have used DuckDB for in the past. But now I can just run ClickHouse local, give ClickHouse local access to a swarm cluster with as many nodes as I need, 16, 32, 64 nodes, each with their own pipeline to S3, and I can run my query really fast directly from my laptop. So this is a specific example that we ran from an actual cafe in Amsterdam. Without swarm clusters, the query took 440 seconds, which I'm not waiting for that, right? I'm gonna close my laptop or move or do something. I'm just not waiting. 440 seconds means I just can't even access the data. With swarm clusters, we were able to run the query in 4 seconds, which is definitely acceptable. I'll wait 4 seconds for a relatively complex query over a very large data set. And once that data was cached in the swarm cluster, I could run the query again in under a second. So this is the power of this compute storage separation architecture. Single sign-on also helps here, right? Because if I can authenticate to all of the Iceberg storage locations as well as ClickHouse with a single authentication, that just makes this whole process much easier, whether I'm initiating it from my own laptop or from a remote API or something like that. So just to recap, we kind of have these 3 things that we have done for Project Antalya that really enable AI use cases as well as just making ClickHouse cheaper and more scalable, right? So it's the hybrid tables on Iceberg that make the storage cheaper without sacrificing latency. It's the stateless swarms that can be located anywhere and scaled up and down as needed. And it's single sign-on to make all of this easier to use and simple. And as I mentioned, everything we're doing is open source. It's all Apache 2.0 licensed, so you can run it anywhere you want. What we've seen so far in terms of actual use cases with AI and where AI is actually useful with these systems, there's sort of 2 main use cases that we're seeing. One of them is code generation, right? Using these AI tools to generate code that is then going to consume these analytics, right? And so using frameworks, there are many open source frameworks that I'm a fan of. You can check out some of the webinars that I've done with some of our partners. This makes it really, really easy to create these analytic workloads because the AI doesn't have to reason about all of it. It can sort of just use the tools in the framework, and you get a deterministic pipeline to manage your analytics rather than having to rely on the non-deterministic and somewhat unpredictable large language models to be doing the processing for you. That being said, these large language models have way bigger context windows than I do in my brain. They're really, really powerful at scanning a huge amount of data and analyzing it for things that might be interesting. And we're finding that this is particularly interesting in the realm of like what might be done by SREs or data analysts, because you can feed in the database schema, you can use an MCP, you can feed in things like monitoring data about your system. You can even use this for monitoring and analyzing other AI workloads, right? And then the agent can give you a huge head start in whatever you're trying to do, whether you're trying to build new capabilities or diagnose a problem. And that's all I've got. So thank you so much.